Did you know that the United States has invested over 15 billion USD in the construction of a single border barrier? This is not a conventional fence designed for a private garden or a construction site. It's the largest fence on the planet, erected to thwart the American dream. Spanning over 3,200 kilometers and reaching heights equivalent to a three-story building, the project represents a significant undertaking in modern civil engineering. The primary technical question is, why were hollow steel bollards selected for this structure instead of solid reinforced concrete? Is this material design sufficient to withstand constant physical pressure and meet long-term security requirements? In this video, Massive Minds provides a detailed analysis of the construction and engineering logic behind this $5 billion infrastructure. We will examine the technical specifications and the structural reasoning that define this project. To understand the rationale behind the $5 billion investment, it is necessary to examine the systemic inadequacy of the previous infrastructure. For decades, the southern border barriers consisted primarily of lightweight civil fencing installed during the 1,990 seconds. In 2019, a record 851,000 crossing attempts were documented, indicating that existing measures were insufficient to manage significant migration pressures. This situation necessitated a $5 billion engineering overhaul. Rather than continuing with ad hoc repairs of obsolete fencing, the United States initiated the construction of a 9-meter-high physical barrier. This structure is designed as a delay system, engineered specifically with steel and concrete. The strategic objective is precise. If total prevention is unattainable, the engineering must prolong the time required to breach the perimeter, providing a sufficient window for rapid response units to intervene. However, the primary technical question remains: why did engineers select hollow steel bollards over solid concrete walls for this specific application? The primary reason engineers rejected the solid concrete wall option involves the significant geological variability along the 3,200-kilometer perimeter. With diverse terrains ranging from unstable dunes in California to monolithic granite formations in Arizona, constructing a continuous concrete foundation has proven to be prohibitively expensive and technically challenging. To ensure the 9-meter steel structure maintains stability against substantial desert wind loads, engineers required a method to securely anchor the base to the geological layers below. In areas with hard, solid bedrock, conventional mining techniques such as using hydraulic hammers prove inefficient in terms of operating speed and risk, compromising the integrity of the surrounding rock by causing fracturing. Consequently, specialized trenching machinery with a 400 horsepower capacity was deployed. Utilizing alloy cutting blades, this equipment penetrates the bedrock directly to excavate 3-meter deep foundation trenches with precise vertical walls. This geometric precision ensures that poured concrete adheres optimally to the original strata, resulting in a robust, monolithic connection. This methodology integrates the bedrock into the load-bearing system, enabling the structure to withstand high wind loads without the need for extensive external bracing or support systems. This approach represents an optimal solution for maintaining rapid construction schedules while achieving maximum structural stability under extreme environmental conditions. Despite resolving the subterranean foundation challenges, the technical question remains: why did engineers continue with the hollow steel bollard design instead of utilizing a uniform concrete wall structure? In practice, solid concrete walls create strategic visual occlusions. In the context of border security, if patrol units cannot monitor activities on the opposite side of the perimeter, they lose operational awareness. This lack of visibility hinders the early detection of smuggling activities or preparations for illegal border crossings. This requirement led to the implementation of the steel bollard design. The spacing between these steel columns is calculated with centimeter-level precision. It is sufficiently narrow to prevent adult passage while maintaining the necessary line of sight for surveillance. This transforms the barrier from a passive obstacle into an active observation system. Border personnel can maintain visual contact and utilize thermal imaging systems from significant distances, allowing for proactive intervention before individuals reach the physical structure. Beyond surveillance, the logistics of transport and assembly in remote desert environments presented a significant engineering challenge. Transporting millions of tons of solid concrete across thousands of miles of unstable sand is logistically inefficient and increases project timelines. In contrast, hollow steel sections possess a superior strength-to-weight ratio. This allows for higher panel density per transport vehicle, significantly accelerating the construction schedule. The installation process utilizes modular assembly. The 9-meter-high prefabricated panels were lowered into pre-prepared foundation trenches using powerful cranes. In high-priority sectors requiring maximum fortification, engineers implement a hybrid reinforcement solution. High-strength concrete and rebar are injected directly into the hollow steel columns. This converts the flexible steel exterior into a reinforced composite pillar capable of resisting standard metal cutting equipment. Finally, the design addresses long-term structural durability in extreme climates. In desert regions, significant diurnal temperature fluctuations cause thermal stress in large-scale concrete structures, often leading to surface fracturing and degradation. Steel bollards, characterized by superior thermal dissipation and elastic properties, maintain structural integrity over several decades, with minimal maintenance requirements. Even with significant height and optimal visibility, a critical vulnerability remains: the potential for tunnel construction. To mitigate this risk, engineers implemented a sophisticated detection and prevention system integrated within the foundation structure. To obstruct unauthorized tunneling operations, the foundation design was expanded both vertically and horizontally into the geological strata. Following the excavation of high-precision trenches by heavy machinery, specialized teams installed high-density reinforcement steel. Thousands of tons of industrial-grade rebar were assembled into continuous, interlocking cages along the 3,200-kilometer perimeter. These cages provide the internal structural framework for a massive, reinforced concrete base, measuring 1.5 meters in width and extending 3 meters below the surface. The 1.5-meter horizontal width of this concrete base serves as a primary engineering deterrent against subterranean breaching. Due to the substantial lateral volume of the reinforced structure, any tunneling attempt must originate from a significantly greater distance to bypass the concrete obstacle. Statistically, extending a tunnel by several dozen meters through unstable desert soil increases the logistical requirements for excavation, soil removal, and structural shoring, which simultaneously increases the probability of surface detection via aerial or ground surveillance. The concreting process was specifically engineered to ensure total monolithic integrity, the creation of a single, continuous mass of material. Once the 9-meter steel bollard panels were positioned within the foundation trench, high-strength concrete with low permeability was poured to anchor the columns. During this process, industrial high-frequency vibrators were utilized to eliminate air pockets and ensure the concrete fully encapsulated the steel rebar and the base of the bollards. This created a high-density synthetic rock mass with superior compressive strength, providing maximum resistance to mechanical breaching or explosive charges. The most critical technological component within this foundation is the integration of a distributed seismic sensor array. Because the concrete base is a continuous, uniform, and high-density medium, it functions as a highly efficient conductor for mechanical vibrations. In physics, seismic waves travel more effectively through solid, monolithic structures than through loose, unconsolidated desert soil. Consequently, any mechanical impact such as drilling, manual excavation, or the use of pneumatic tools generates distinct seismic signatures that are transmitted through the concrete foundation. These vibration signals are captured by the embedded sensors and relayed to centralized command and control centers. Advanced signal processing algorithms are employed to triangulate the source of the vibrations with a high degree of spatial accuracy, distinguishing between ambient environmental noise and intentional mechanical excavation. The barrier thus functions as an active acoustic monitoring system. Any detected subsurface intrusion attempt triggers an immediate operational alert, allowing rapid response units to intercept the operation before the structural integrity of the perimeter is compromised. By utilizing this multi-layered geotechnical methodology, The engineers have rendered the cost and technical complexity of tunneling prohibitively high. To protect the $15 billion infrastructure investment, engineers had to ensure structural longevity under some of the most demanding environmental conditions on Earth. The 3,200-kilometer borderline is not geologically or climatically uniform. It extends from the California coastline, characterized by high atmospheric salinity, to the desert basins of Arizona. In these regions, the structure is subjected to extreme diurnal temperature fluctuations, where surface temperatures can exceed 50 degrees Celsius during the day and drop below freezing at night. Without a specialized protection system, the high-volume steel components would undergo rapid oxidation and corrosion, leading to significant structural degradation within a few years due to exposure to salt spray, humidity, and abrasive wind-borne sand. The industrial coating process begins during manufacturing, adhering to rigorous engineering standards. Instead of conventional surface painting, each steel column undergoes a comprehensive hot-dip galvanization process. This creates a permanent metallurgical bond between the zinc and the steel, covering both the interior and exterior surfaces. Subsequently, a specialized polymer powder coating is applied via electrostatic spray to provide a durable brown finish. This multi-layered system functions as a chemical barrier that prevents direct contact between the steel and environmental oxygen or moisture. This technical approach is the primary factor, allowing the structure to maintain its integrity for several decades without requiring frequent or complex maintenance procedures. However, environmental durability is only one requirement. Engineers also address the mechanical challenge of preventing the structure from being scaled. Despite the 9-meter vertical height, the barrier remains vulnerable to specialized ladders or advanced climbing techniques if anchor points are available. To mitigate this risk, anti-climb plates consisting of smooth, flat steel panels were integrated at the summit of the structure. When a person attempts to scale the 9-meter height, they encounter these smooth steel surfaces, which are designed to eliminate all possible handholds, mechanical hooks, or other anchor points. At a height equivalent to a 3-story building, the lack of friction and grip makes unauthorized climbing technically difficult and poses a high physical risk to the individual. In high-priority sectors, military-grade concertina wires installed behind the crest as an additional physical barrier to further obstruct passage. The entire construction sequence, from the utilization of specialized trenching machinery for bedrock penetration and the high-visibility bollard design to the seismic integrated foundation and the multi-layered protective coatings, transforms the project into a complex engineering system. It represents the integration of structural mechanics and strategic logistical planning. This demonstrates that when engineering is applied with pragmatic precision, it is possible to create durable boundaries that maintain their functional requirements against both environmental stressors and external physical challenges over a long-term horizon. Following several years of high-intensity deployment and the allocation of vast federal resources, the border wall project has yielded a series of documented outcomes and controversial consequences. By January 2021, approximately 729 kilometers of the structure had been physically completed. However, the financial price of this fortification was substantial. Total actual expenditure surpassed the $15 billion threshold. This figure solidifies the project's position as one of the most expensive and logistically complex infrastructure undertakings in modern American history. From an economic perspective, the intensification of border controls has sent direct shockwaves through the southern border states. The regional agricultural sector, which has historically operated on a low-cost labor model, is now contending with acute workforce deficits. The resulting increase in production costs and the disruption of established labor supply chains have forced many agricultural enterprises to restructure their operational models or, in some cases, significantly downsize their production capacity. In addition to the economic shifts, the natural ecosystem has sustained irreversible damage. The 9-meter-high steel barrier has effectively severed vital migratory corridors for indigenous wildlife, including species such as the jaguar and the bighorn sheep. This habitat fragmentation has triggered a series of prolonged legal challenges from environmental conservation organizations. These ongoing litigations have created significant legal and administrative hurdles, complicating the long-term maintenance and operational oversight of the project. The most profound impact, however, is observed on the security front. While the physical barrier has successfully increased the time required for manual crossing attempts, it has not halted clandestine movement. Instead, it has inadvertently accelerated a new technological arms race. In response to the wall, transnational criminal organizations have transitioned to more sophisticated and elusive methods, such as utilizing unmanned aerial systems, drones, for smuggling and deploying semi-submersible vessels for maritime transit. The strategic landscape has shifted. The conflict is no longer merely a matter of steel and concrete, but a competition between seismic sensor arrays and surveillance radars against the high-tech equipment of organized crime. Consequently, the U.S.-Mexico border wall functions as more than a simple physical obstacle. It has become a symbol of the pragmatic efforts, the immense expenditures, and the unresolved challenges faced by a global superpower attempting to maintain territorial integrity in a rapidly changing modern world. The border wall project is no longer limited to physical barriers. Engineers have defined the structure as a foundation for integrating high-tech surveillance systems. Border security is currently shifting away from a reliance on only steel and concrete toward the implementation of AI, ground scanning radar, and persistent drone patrols. The fundamental objective of this integrated system is to maximize the time required for unauthorized entry while optimizing the response time of security forces. Although the project continues to spark debate regarding its fiscal and social costs, the wall serves as a significant case study in extreme-scale mechanical engineering. With a total investment of $15 billion, the project has established a new benchmark for combining civil engineering and pragmatic security tactics. It currently stands as the most fortified physical barrier constructed in modern history for national border control. In your opinion, is the $15 billion investment in this steel wall system an effective security solution or a high cost compared to reality? Please share your perspective in the comments section. If you are interested in the construction processes of global megastructures, please subscribe to Massive Minds and turn on notifications to follow our upcoming technical analysis videos. Thank you for watching.